Hi, my name is Manish Gupta, and in this video, I'm going to talk about GZXML or ZestXML, which is basically about generalized zero-shot extreme classification or extreme multi-label classification. Okay, let's get started. Let's first understand what is this problem of GZXML, generalized zero-shot XML. Okay, so the idea is that in a typical extreme classification problem, labels belong to different data regimes and they need to be accurately modeled in a seamless manner. So there are some labels for which there are lots of training data points. We'll call them as many short labels. Then there are some labels which have a few data points. We'll call them as few short labels. Basically, let's say 1 to 3 data points. And then there are some labels which have zero training data points, and we'll call them as zero short labels. So they have zero training data points. Okay. So now predicting completely unseen labels with no training points is a very difficult problem, right? So as is extreme classification is a difficult problem, but then imagine coming up with more labels that you need to predict at test time rather than seeing them at train time also. Okay. But the problem or the interesting part is that zero shot predictions are so commonly required by various applications. So, for example, if you think about um, the problem of mapping a query to a document or mapping a query to a advertisement, right? New ads keep coming up every day. So there is fresh and personalized information that is desired by users, which basically means that there could be several unseen labels which are naturally required to be supported by such extreme classification applications. Okay. So in short, what is GZXML? It is basically the problem where relevant labels need to be chosen from all available seen as well as unseen labels. So you may need to come up with, predictions for unseen labels as well. Okay. And then given those seen and unseen labels, one has to basically choose which of them are relevant. Okay. Now, the other point is that if you just look at popular labels, they might not have enough data to allow complex and personalized models. The tail labels require information. They might have enough data. So if you really talk about popular labels, they may have enough data. But if you think about tail labels, whether it is few shot or zero shot, they require information sharing between labels. Without information sharing, there is no way that you can actually predict them as relevant. Okay, this plot basically just shows you what is the number of labels associated with different number of previously clicked ads per query. So on the y-axis you have number of search queries, and on the x-axis you have number of previously clicked ads per query. And what you observe is that there's a long tail. So most queries have few or no previously clicked ads, right? So essentially, if you think about it, a whole bunch of queries essentially here have no previously clicked ads. So basically meaning if you're trying to take an ad and try to figure out the keywords or key phrases for that ad as labels, you have this zero shot or few shot problem where there are only a very few number of training data points available or no data point at all where you consider queries as labels. Okay. Okay. So now how does the training happen in this algorithm? So the algorithm is actually called as ZestXML. So, the algorithm is called as ZestXML and the problem is called as GZXML. So for zero shot XML, how does ZestXML work? Yeah. To understand this, the setup is actually pretty simple and pretty clean. So let me just go over it very quickly. So N is the total number of training data points in the data set. L is the total number of labels, and xi, each data point is embedded in a space of size c. So that's the number of, so for example, if you're using TF-IDF sparse representations for xi, your c could be, let's say, 100,000 because your TF-IDF vector could have vocabulary size of 100,000. Okay. So ZL basically is the text associated, is a representation associated with your labels, and it's basically in a high dimensional space D. Okay. Now, again, if you're using the same sparse TF-IDF vector representation, it could also be 100,000 in that senses. Okay. So they are both sparse TF-IDF feature vectors. Okay. Now, so therefore, if I think about it, the matrix X, which basically contains data, is essentially of size n cross c, and the matrix, if I care about the labels, well, the label matrix essentially is of size L cross D because L is the total number of labels and D is the dimensionality of those labels. Yeah. Now, YIL basically denotes whether the label L is relevant to the data point I or not, and therefore it can take just two values, -1 or 1. Okay. Now, in ZestXML, the way the problem is sort of attacked is by considering relevance between a data point I and a label L. Okay, so the score is defined as xi transpose WZL, and that's sort of pretty reasonable. So the way to understand this is as follows: you essentially take the original data point xi and multiply by W so as to map it to the data to the label space, and then you multiply. Multiplication typically stands for similarity or relevance, and therefore you multiply this xi transpose W with ZL so as to identify how similar or how relevant the label L is to the data point xi. Okay. Um, Now, to be able to learn this W, a way of projecting X onto the label space, a way to learn this W is by solving this regularized logistic regression problem. Okay. So what you want to minimize is the errors. So this guy basically, this is basically logistic regression, right? So it's basically the same logic and then the logistic loss. Okay. So you want to minimize that across all data points and across all labels. And of course, you want to regularize W. You don't want your W to be very large. And therefore, you also regularize the Frobenius norm of the W matrix. Okay. That's that. Now, one other extra constraint that they have added is to ensure that there is sparsity in the W that is learned. Now, this sparsity is super important for efficiency later and also for high quality. Okay, so we'll talk about this efficiency bit slightly later, but the idea is that you basically have enforced a constraint that every row of W should have maximum K as the overall sum. Okay, so the L0 norm of every row of W has been constrained in that sense. Okay. So of course, K and lambda are two hyperparameters to be tuned in this algorithm. Uh, each row in W has only a handful of active voters, basically meaning only a handful of these K which are active. And in the setup, they basically set K as approximately 10, which basically means that each row of W has, up to 10 different 10 different voters, 10 different values which are non-empty. Okay, for a given data point. Now, basically, less number of entries active in a particular W basically means small number of label features are triggered for any data point, and that makes sense because for most data points, a small number of labels are applicable. Okay. Um, So although this formulation basically with the L0 constraints makes it super nice in the sense it has naturally modeled the problem, the L0 constraints actually make this problem non-convex and therefore NP hard to solve. Okay, which basically means that it would make it very, very inefficient as a solution. Okay, so therefore the paper actually proposes a two-step efficient process, which is called as extreme hard thresholding pursuit. Okay, now I'll not go into the details of this process, but it has two steps essentially. And by the way, this hard thresholding essentially just basically refers to the hard thresholding constraint, which is put up here. Okay, so basically it has two steps: approximation and refinement, and I'll not go into the details of that. Look at the paper if you're really interested. But the point is that the approximation step is going to give you a first output WA, I mean first estimate of this matrix W, and then the refinement step refines it further so as to give you the final WR matrix. So basically, you could directly use WR at prediction time. That's the idea. Okay. Now, how is inference done in this ZestXML algorithm? Well, the inference is done as follows. You want the inference to be done in small amount of time. Remember, the number of labels are large. If one were to essentially, do inference across all set of labels, it would take insanely crazily large amount of time because L is very large. Number of labels is very large. But what you typically want is log L time, right? So essentially O of log L time. And therefore, they propose to use inverted indexes so as to make the processing much faster. So inverted index, what do you store in inverted index? Well, you store label features as keys and labels themselves as values, right? So here label features, since it's TF idea, it basically is just words. So basically for every word, you essentially store what is the full label associated with this word, okay? Now, when a test point comes in, you essentially project that test point into the label space by doing W transpose X, okay? And then for every non-zero element in this transpose revised representation, for every non-zero element in this revised representation, you're going to look up the inverted index for that particular word, get the labels, overall set of labels which are relevant, and then you aggregate the label scores across all of them and return the top K label. So it is as simple as that. Okay. So basically, inference is essentially supported by inverted index. However, if you were to do this kind of inference, this W transpose X operation can be super expensive. Okay. Um, so you could basically use WR directly, but WR can be super expensive. Now, why is it super expensive? Because some inverted indices, some of those indices corresponding to popular label features might be very long and therefore contain many irrelevant labels. Okay. And that is a typical problem with retrieval. Some of those inverted indexes can be very long, for example, for stop words, right? And they actually can contain many irrelevant labels. And this basically means that the overall prediction procedure can be very inefficient if you just do it as W transpose X, where W is WR, the final matrix that you obtain from the second step in this process. Okay. And therefore, even for inference, the ZestXML algorithm proposes a two-step prediction. Okay. The first step of the prediction is first stage of the prediction. Essentially, you do not use WR, but you use WA. Okay. So WA matrix, essentially, using this WA matrix, you shortlist up to 100 relevant labels. Okay. 100 potentially relevant. Of course, you don't know if finally they are relevant or not, but you shortlist just potentially relevant 100 labels. Okay. And then in the second step, you tune it further by re-ranking these labels using WR-based scoring. Now, the way WA and WR are, the way they are designed, the idea is that each of these steps is very efficient by itself, leading to an overall efficient two-stage inference. Okay. So the first step is basically just called as ZestXML XHTP, and the second step is actually called as ZestXML tuned. Okay. Now, how does this algorithm perform? How does ZestXML perform, on experiments? So, the paper shows experiments on several public data sets as well as on proprietary Bing sponsored search ads data set. Okay. So what do you observe? So broadly, first you observe, here are results, training time, test time, model size in GBs, right? On two data sets, Wikipedia and Amazon. Okay. And comparison is done across several other popular extreme classification algorithms. Okay. So the first thing that you observe is that, if you look at the model size, then the model size for ZestXML is basically the smallest, right? So it has the most compact model and it has comparable training and prediction times. So if you basically look at ZestXML's times, well, it is, it is sometimes higher compared to some other algorithms, but, it is reasonably comparable and practically still feasible. Okay. The other thing that we observe is that if you look at accuracy matrix from, I'm just showing you accuracy matrix for Wikipedia 1 million data set, a PSP matrix, that too, and, comparison with several other, extreme classification as well as dense retrieval kind of baselines, right? If you compare, you basically observe that the accuracy metrics are highest or close to highest PSP. Okay, so that's that. PSP typically focuses on the tail. So this basically means that yes, on the tail, you're actually getting way better, way more accurate results. Okay. Now, if I basically look at zero shot labels versus few shot labels, so this is basically the same performance for Amazon dataset split into two kinds of labels: zero shot labels and few shot labels. What you observe is that ZestXML performs really well on zero shot as well as few shot labels also. So it consistently outperforms baselines across both zero shot and few shot labels. Uh, so specifically in zero shot, it was able to give really good results. Other algorithms did not really work. So other algorithms are not shown because they are not capable of doing zero shot classification anyway. Okay. So that's that. So now more on sponsor search ads. So I'm not showing detailed results here, but the idea is that in sponsor search ads, the broad idea is to be able to take the query and do a retrieval of relevant ads. Now, typically the way this is done is basically using inverted indexes. You take each of those words, figure out ads that match those words, and do inverted index kind of stuff, retrieval, right? However, what GZXML or what ZestXML allows you to do is to not look up just by the original words. You look up, you have a very different inverted index structure, right? You basically look up by multiplying W with X with W. So bring the overall, transform the overall query space into the label space, and then do this inverted index lookup in some ways. And of course, it also improves the overall efficiency of the inverted index lookup. So it sort of improves the inverted index creation and also lookups in that senses. Okay, and after deployment on Bing, people found that it improved the click yield of the information retrieval based system So the default system was information retrieval based system, BM25 and so on, right? It improved the click yield by 17% and unseen query coverage by 3.4%, which has had a significant revenue impact as well. Okay. So here are some examples to show you how GZXML performs. So what you see here is essentially the original product, and here the ZestXML algorithm is being used so as to recommend other related products. This is on Amazon dataset, so it's basically product recommendation dataset. Okay. So what do you observe? So the original input is the maker's diet for weight loss. So that's basically the original product, and these are the products which have been recommended by ZestXML. The tick marks basically show that they are in the ground truth as well. Okay. So as you observe in all the four cases, essentially most of them are in the ground truth. Yes, some of them are not in the ground truth, but they are still very reasonable recommendations in that senses. The other thing to observe is what is the debug information that is shown here. So top active instance label feature pairs. So the idea is that thanks to the learning, GZXML sort of learned that maker diet sort of relates with labels like restore digest, program transform, maker diet itself, and heal thyself, and so on. And that is why it was able to come up with these labels as predictions. So if you basically see restore and digest is being used here, maker's diet, of course, matches the maker's diet. But then there are other kinds of keywords which ensured that these products turned up at the top, even though you may not have um, I mean, even though these were like zero shot, even though you may not have these as recommendations for any training data points. Okay. So in summary, in this video, I talked about a problem called as GZXML. So generalized zero-shot extreme multi-level classification, which is a problem of zero-shot labels in XC. Right. We also talked about ZestXML, which is basically an algorithm for an extreme classifier to solve the GZXML problem. ZestXML essentially learns a highly sparsified linear transform W, right, between the data points Xi and the label features ZL through an innovative optimization technique. I talked about that two-step optimization technique, right? And on experiments, people have found that it can be up to 14% and 10% more accurate relative to leading extreme classification and dense embedding-based approaches, respectively. Right? On sponsor search ads on Bing, people found that compared to an information retrieval baseline, ZestXML actually improved the click yield and unseen query coverage by huge margins, 17% and 3.4%. Okay, that's it for this video. Hope you liked it. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.